Hello, can you hear me? It's working? Can you hear me? No, but not from my gosh. Hello, hello. Can you hear me? No. Can you hear me? Yes. No idea why this microphone is not working. I'm gonna try to do my best with this, but sometimes I sort of move my hands a lot. So if the sound is not going through, just let me know. Yeah. How are you guys? So what happened to the people? Last time I was here, this was full, and now it's half, maybe quarter full, not so full. I'm going to assume that because it's Friday, it's raining, the World Cup match today maybe, or maybe you are working in the assignment, which deadline is next Friday, actually at 5 p.m. Are you working on that? Are you? Yeah, if you are not, please do as soon as you can, okay? Sorry, you have a question? Oh, no, okay. I thought you had a question. Remember, deadline is next Friday, 5 p.m. And also, by the way, remember that you would need to have discussions with your tutors after you submit the assignment. These discussions are planned to be during week 6. So please engage with them, with your tutor, to see and to check when exactly that is going to be during that week, okay? Nevertheless, I can tell you at the moment that you can see there the last second, sorry, the second last, sorry. The second last icon there saying assignment 1 bookings. You cannot see it now, so we are going to be opening that possibly closer to the deadline, and in that moment you are going to be able to book an appointment with your tutor as well, okay? Good. Okay, so in the previous weeks, you have reviewed with Oliver different artificial intelligence approach. I would say more classic AI, no? Approaches like search, planning, knowledge representation. But today and the next week, these 2 weeks, we are going to be talking more, well, approaches closer to machine learning or in machine learning area, okay? The first one, the one that we are going to be reviewing today, is neural networks. Is there any of you guys has any knowledge already about neural networks? Good. Okay, because I'm asking this because I know sometimes some people is taking this course and in parallel the artificial intelligence course. Which is, in my opinion, not the best case scenario, because, well, here we are going to be covering the basics concept. We are not going to go that deep. Obviously, it's only one lecture. The other one is just a full course. But the idea, well, pretty much for the whole discourse, no, is that you can have a general idea about the topic, and then later, if you enjoy whatever area of AI, you can go deeper taking an additional course, okay? Good. So let's talk about neural network today. I'm going to move this. So we are going to be seeing today, well, quickly motivation, very quickly, a very quick comparison with the biological neuron as well, a couple of different architectures, particularly the single-layer architecture called single-layer perceptron. An extension of that, which is called multi-layer perceptron. We are going to be seen also the neural network design, which is going to be relevant particularly for what you are going to be doing next week during the tutorial. Then maybe a quick conversation about others neural network architectures, okay? Okay, let's start with the motivation. Okay, the main motivation here, and well, you can extend this possibly from AI, no? At the end of the day, if you remember when we talked about AI in the introduction, I said, okay, what is intelligence first, no? And then we said, okay, and then now, what is artificial intelligence? Well, here you can extend as well the concept of artificial neural network from biological neural network, okay? Why? Because, well, the biological neural networks are present in cognitive beings, to say humans, but also animals, okay? And we have seen that they have great skills, great capacities to solve some problems that are present in nature, okay? They have great ability to adapt, okay? And to do that, they use certainly their own neurons, okay? Some of these tasks are, well, sometimes more difficult for machines than for cognitive beings, okay? And it's, in my opinion, it's sometimes funny that, well, AI or in general machine learning approach can solve some very difficult problems really effectively, but sometimes very easy problems for us could be problematic for machines, okay? Therefore, we are in this context, we are going to be trying to emulate, well, first understand and emulate this mechanism which is present in the human brain, again, not only human, but cognitive beings' brain. Particularly, we are going to try to mimic this highly parallelism and high connectivity, okay? So this is a branch of artificial intelligence which is called artificial neural networks. Well, here, when we talk about, well, the classic algorithmic point of view, it's something that we call, well, it's based in the very classic von Neumann machine, no? Which is basically the execution of every instruction sequentially, no? One after another, or maybe you can have a loop or condition, whatever, but you go one by one, no? Here the idea is non-algorithmic processing, so we call this neurocomputing, in which the information of the processing is the information fluency and the processing is done in a parallel way, okay? Nevertheless, there is a cost. We are going to talk as well later, again, when we talk about the neural network design, that particularly in the sense that, well, neural networks are very effective in many domains. Nevertheless, they are not silver bullet. They are not able to solve every single problem just trying to use them and put it in to solve a problem. We need to take into consideration a few things before decide to use it, okay? And one of the particular issues that still is an open problem is, well, generalization. So, well, we need to understand that neural networks are indeed empirical models in contrast to phenomenological models, no? Empirical models means that they are highly dependent on data. We need data and good data to train these models. And still, we are going to be able to do, well, maybe good inference, not necessarily in a general way, while when we use phenomenological models, also sometimes called white box models, they are, or they can easily generalize to other different domains, not domains, but let's say data that has not been seen before, okay? Okay, but that's a part of possibly another class. Okay, neural networks are models, just like I said, they are empirical models, no? But if you compare with phenomenological, there are obviously differences, but they are models anyway. You are going to have input, something which is processed, and then outputs, okay? In that sense, we say that neural networks are function approximators. Therefore, they can approximate whatever nonlinear function with an arbitrary precision, okay? Again, some things to consider in some slides from now, okay? But they can work in two different ways to solve two different problems. One is as a classification problem, and the other one is regression, okay? When you use a classification problem, what you want to use the network or the neural network is to discover what class an input belongs to, okay? So regularly there, obviously you are going to have discrete outputs. Could be maybe only one output. You can classify binary, like belong or not belong, but you can also have multi-classes, okay? In any case, you are going to be working there in discrete, possibly, mostly discrete scenarios, okay? While when you are talking about regression problems, in this case, you are going to try to approximate the generating function, which it's going to work in a continuous domain, okay? So for instance, you want to predict what is going to be the temperature in all the coming hours, or the coming days, whatever. You can have a plot in which you are going to have continuous values from now onwards, okay? But that's different. You are not classifying it is going to be rainy or not. That is classification, okay? The other one would be regression, where you have continuous values from now on, okay? Okay, so let's quickly talk about the biological neuron, the biological and the simul with the artificial neurons, okay? If you saw biology at school, maybe you saw this model already. This is the general, there are different figures, but this is the general model for a biological neuron. Things that you can, or you should observe here are, at first place, dendrites, okay? They are the input for the neurons, okay? So all the information is actually coming through dendrites, which in this case, as they are biological neurons, are electrical pulse, okay? What you have here or here is cell body, or sometimes called soma as well. Inside there, in the body of the neuron, is where some electrical or biochemical process may happen. And if you go beyond a particular threshold, a signal is put here in the output through the axon. Okay? So when this output is sent through the axon, that is going to become the input of a next neuron, okay, of the input of another neuron, okay? And in these inputs here could be go through something which is called synapses, okay, which means that could be a process there that is going to be inhibitory or excitatory, make it this, in simple word, make it this input like bigger or lower, okay, incrementing or decrementing that input. And then, same thing, biochemical process. If there is, if the potential inside go beyond a threshold, an output is sent through the axon and then to another neuron and so on. Okay, that is very simplistic explanation. Of course, I'm not a biologist, but this is the general way in which this works. Okay. Well, some things, we already defined soma, dendrites, axon, and synapses. Yeah, look, the synapses, as said here, can be excitatory, inhibitory. I already mentioned that, but importantly, and I didn't mention before, they may change over time, okay? This is actually crucial as well when we see the artificial model, because the weights of the network, it's another way to call, sometimes called like synaptic weight. Okay, and this is something that we are going to adapt during the training or learning process. Okay, and this is the electrical pulse through the axon as well. A couple of facts. Okay, in the human brain there are around 10 to the power of 10 and 10 to the power of 11 neurons. Okay, which obviously is a lot. But more interestingly, some of them, well, in average, they have 10,000 synapses, and some of them until 100,000 synapses. Okay, so if you consider this, that only one of these neurons can be connected to 10,000 others in a network which is going to have 1 billion of 100 billion neurons, the level of parallelism in the brain is massive. It's really massive. It's huge. Okay? We said here, well, that the latency is 3 to 6 milliseconds, so you can say, well, it's actually not that quick. True. But the thing is, the massively parallel processing make that that they are quite effectively, no? Okay, if we take this into account, we now can define the artificial neuron. Obviously, the artificial neuron that we are going to be using here is not really exactly copy of the biological one. It's rather inspired from that, and also the way that you can connect them, no? Okay, so the artificial neuron is going to be characterized by an internal state, some input signals, and activation and transfer functions. We are going to define those. But before, we are going to see this very old model from 1943, proposed by McCulloch and Pitt, okay? In which this artificial neuron is proposed as a simile of the biological one, okay? Well, here you will have x1, x2, xn, and different inputs. Well, if you make the simile with the biological neuron, these inputs, you can say they are dendrites. What you have here, if you see, is a weight which is weighing this input, okay? So if you consider this function here, we are going to say that this, they are going to call the output here A. So A, it's going to be the summation of x e weighed by this value from 1 to n. Okay? So every input, it's weighed by this value, which is called sometimes which is called synaptic weight. Okay? This is the name, but regularly we call it weight, or many times as well, parameters of the weight of the network. Okay? These are the parameters. If you see this value A, so we can say that this is actually the body has these two different functions. Okay, one is called actually called activation, and the other one is a transfer. functions. But what you can see here, it's similar to the action potential, when we say that if you go beyond a threshold, a signal is sent through the output. And the output is this one, which would be the axon. Okay? And this function here, well, in this case, is called the step function. So for the output for this model is going to be either 0 or 1. Okay? It's going to be 0 if the value going out of the summation, the value called there A, it's lower than the threshold, it's going to be 0. If the A value is higher than the threshold theta there, it's going to be 1. Okay? Is that clear? Or not so clear? Let's see. Okay. Keep. Okay. So imagine that you want to use a neuron of McCallum and Pitt to model the logic function AND with 4 inputs. So you went to model AND 4 inputs. Okay? Well, when the logic AND is true, consider you have 4 inputs now, which are going to be logic values, like true or false, when the output is going to be true. Well, each of them, all of them are true, no? Sorry? All of them, exactly. Correct. That's correct. So I'm not going to draw here the full table, but we're going to consider x0, x1, x2, x3, and then you can say maybe all possible variables or combinations. Okay? And then AND, as you mentioned, is going to be 0 for all cases, except the last one. Okay? If you consider this function, and we are going to consider as well here, we didn't say, I'm going to say it now, for simplicity at the moment, I'm going to say that all weights are equal to 1. Okay? Okay, so we want to know how much is going to be A, no? So we said that A is going to be that one, no? Therefore, here A is going to be, well, 0, it's going to be 1, it's going to be 1, it's going to be 2, it's going to be 3, it's going to be 4, perfect. Okay, so the output, we know is 0 or 1, no? So it's 0 if the value of A is less than theta, or so the question is then now, what is the value of the threshold? For instance, because yeah, 3.5 could be because, well, actually any value between 3 and 4, no? Well, something that divided this between when it's, well, the value is when it's 0 or where it's 1, no? Therefore, you could say actually that theta is 3.5 because this value is linked with this threshold, no? That's correct. So quickly, what if I want to use same, Mercado and Pitts, for an OR with 3 inputs? And all weights equal to 1. Okay, go quickly and tell me how much is the threshold. You have 1 minute. That's quick. That's quick, and it's correct. How much it is? That's correct. How much it is? But again, as before, you need to find a way to divide these different inputs, no? Now you have 3 inputs, same question as before. When, in an OR function, the output is going to be 1? When? Or giving 3 logic inputs, true or false, what do you need for having a true in the output? What do you need? What do you need? Exactly, at least 1 true. So quickly, same thing as before, you could have x0, x1, x2, and 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Well, I can write this one, it's shorter. Okay? For OR, this is going to be 0, but all the rest is going to be 1. Okay? So if you consider, again, weights to be 1, the activation value is going to be 0, 1, 1, 2, 1, 2, 2, and 3. But as you can see here, you need to find a way to divide here. Therefore, similarly as before, you can say that this is going to be 0, this is going to be 1, when A is lower than 0.5, actually more than 0.5, it's going to be 1. Okay? So the threshold now is 0.5 because you need to look at where you split here. Okay? Good. Last one, I promise. Exclusive OR. 2 inputs. The exclusive OR, x0, x1, 0, 0, 0, 1, 1, 0, 1, 1. This is actually 0, 1, 1, and this is 0, because exclusive OR. Okay? What is the threshold? 1.5. Actually, no. But keep trying. Do you have any other guess? Well, it doesn't matter much because there is no threshold. And the idea to make this small exercise with you is precisely trying to show you one was the problem of neural networks many years ago. And I think we talked as well when we did the introduction about something which was called the winter of AI, in which we mentioned that many funding agencies were not given money for research for AI, AI and particularly neural network, because they were considered not to be good enough, because they were shown that even in small problems like the exclusive OR, they were not able to solve. I mean, there is a way to solve, but at that time, they didn't know how to do it. No, that's something that came later. And we are going to mention that as well in a few slides. But why this doesn't have solution? Because if you see the activation values here, considering same setup as before, here you can say that this is going to be, well, 0, this is going to be 1, 1, and 2. Now, the thing is, you should divide here and here, okay? And in this setup, I mean, look, you could solve using this kind of neurons the exclusive OR, but not with a single layer, okay? As we are working here with this setup, this only works when the classes that you want to divide are linearly separable. If they are not, you cannot. You are not going to be able to find this hyperplane that divide the space in two. Okay? So this one cannot. Is that clear? Okay. I guess this is pretty much a summary of what we have seen before. Well, inputs can be 0 or 1, same for the output. You could have weights positive or negative, therefore excitatory or inhibitory. We just, to simplify, said everything is 1 at the moment. When we talk about the single layer perceptron, we are going to see a rule in order to learn this weight, actually. Yeah, sort of the same. Okay, learning. The thing is, one thing is, if you put particular weight to the network and compute the output, okay? But if you know the weight values, it's simply a mathematical problem, no? It's basically to make the computation and see what is the output. Well, it's going to happen that what you are going to be getting at the output, it's not necessarily what you want to get. And then the process is going through a learning procedure, okay? In order to learn what are the right or good weights or good enough weights in order to have something what I really want at the output, okay? So this is a process in which you adapt the weights or adjust the connections, okay, in order to obtain what you really want in the output or to meet a particular criteria, okay? This is based in the Hebbian learning. I'm going to read this. When a neuron A persistently activates another nearby neuron B, the connection between the two neurons becomes stronger. Specifically, a growth process occurs that increases how effective neuron A is in activating neuron B. As a result, the connection between those two neurons is strengthened over time. Well, actually, this could happen in both directions. Well, if you have one neuron continuously activating another one, what is said the Hebb rule is this connection is going to be affected. Okay? It's going to become stronger. In other words, it's going to be adapted over time. Okay? And this is precisely what we want to, well, this obviously applies for the biological neuron, but we want to have exactly the same process in artificial neurons, okay? To find a way to adapt these connections, particularly when one neuron is continuously affecting the other, no? So, now that we know what is one artificial neuron, we should extend this into a network of them, okay? So we said here, information processing architecture, loosely modeling the brain. Really loosely, because obviously, as we said before, the number of neurons and the level of parallelism that is present in the human brain is huge. So here we are not going to have something at that level. Nevertheless, we are going to try to connect and adapt weights in neurons in a similar way. Okay? We are going to have many units, sometimes called, we refer to as neurons. Well, they are going to work in parallel, therefore the information is going to be through the network. And, yeah, here. What we need to have to characterize the network is the number of neurons that are going to be involved, how they are connected, therefore the architecture of the network, the weight value, what is going to be the weight between different neurons, and activation and transfer function, to say how the information is going to go through the network and through the neuron in particular. Okay? Well, this is also still important. Another way to view a neural network, I've said before, they are universal approximators, but another way to see them is that they are able to map input to output. Okay, so you can take whatever data in one domain into another, making this mapping through the network. Okay. So, similar as the previous architecture, so this is also for one neuron, so you will have the input weights. We are going to be weighting these each of these inputs. You are going to have here the transfer function and the activation function. I have to say, though, that particularly in old books, you may find these names in the other way around. You may find that sometimes the first one is called activation function and the second one is called transfer function. But nowadays, I think these are the most common names, no? Transfer here and activation here. Okay? Well, the weights, we said before, they can be either positive or negative, but they are going to be changing over time as they adapt during the learning process. The input is weighted well for the different weights values, and the weights value you apply a function which is in this case this one, no? This function, depending on the network, the neuron, etc., may be nonlinear as well, a nonlinear function as well, regularly, but could be also linear, okay? Okay, so what you see there is a very simple neural network architecture. It is possible, anyway, one of the most used over time. I mean, even nowadays, they are highly used. This kind of architecture is called multi-layer perceptron, okay, or MLP for MLP, for multi-layer perceptron. We are going to review with more details later. But if you, in this particular case, the particular MLP architecture is 2 times 3 times 1, which is also described here. Okay. So we have, in this case, I'm going to say this first, and then I'm going to explain. We have here 3 layers, but actually we have only 2. This is called the input layer. the input layer, which is called the hidden layer, and the output layer. Okay. Every unit there with the f of x is actually a neuron. You already remember, you know a neuron, there is the inputs, the weights, the inside the neuron, the activation and transfer function going to the output. Okay, so each of them is doing precisely what we have seen in one neuron. Okay, I said before that there are three layers, the input, the hidden, and the output, but actually there are only two because the input layer is regularly called like that, as a layer. But if you see as well there is no processing units. There is no neurons. It's just the input which are directly connected to the hidden layer. Okay? So even though it is called a multi-layer perception of 2 times 3 times 1, in the first one here is the input layer, in this case just 2, and I'm going to explain why there is another one in 1 second as well. But 2 inputs, which are coming from the external, and they are connected to the hidden layer, which could be our first layer with neurons, and then they are connected to the output layer. Okay? So this here is where activation and transfer is happening. Okay? So that's why we say 2 inputs, 3, 1, 2, 3, and 1. Additionally, there is this another input which is present here, but also here. It's the same. Okay? This is called bias, and bias is an additional input which is present in this network, which is connected to every single neuron in the network. Okay? So that's why this additional input in this case has 3 connections to the network in the hidden layer, and here 1 to the network, to the neuron in the output layer. Okay? This additional input, well, I'm going to say that the benefit is twofold. No? One, it's, well, regularly you can improve the network performance, but also you can shift the neuron transfer. No? It's, imagine this like you can actually move the threshold that you have from the previous architecture, so you can move this around that axis. Okay? Okay. A neural network, just like the previous one, could work in 2 different ways. One, and the most difficult, is learning. When learning, a neural network can learn in different manners. Here we are naming 2, like supervised learning and unsupervised learning. Okay? Supervised learning means that you will provide examples of input and output. Okay? You are going to have a data set, and you are going to try that the network can map these inputs into output. So every time that I provide the network with an input, I want to see that output. I'm going to give examples, many examples. Okay? Therefore, the network is going to try to minimize the error in the output by adapting the weights parameters, okay? Changing those in order to obtain what is the successful criteria in the output, okay? On the other hand, you also could work in an unsupervised manner. In that case, you also need data. They are still empirical models. You also need data, but in that case, the neural network will not have examples or samples for the output. Okay? Regularly, you use this data just as an input and trying to find different patterns that may be present in that data. Okay? For instance, if you want to identify different clusters, no? to see what data is similar to other and maybe build particular group or classes from that input data, okay? All in all, coming back to learning, either supervised or unsupervised is indeed one of the most critical process during the use of neural networks. I'm going to come back and talk particularly with more details about the learning process when we talk about the design design of neural network, the one I told you that you will be using during the tutorial, because there are many other things to say certainly about the learning process. It's a hard process. Regularly, it's computationally expensive as well, time demanding, and it's critical in the sense that you not all the time are going to be able to find good results in that, okay? Now, if you were able to do or perform a good learning process, now you can say, okay, what if let's focus in the supervised learning. Let's say that I provide samples. I train the network successfully, okay? So now I could go to the second stage, which is simulation or recognition. No? In that stage, or inference if you want. In that stage, I'm going to use the neural network, which is already trained. Therefore, the network knows what to put in the output if I provide an input. Regularly, I'm going to give an input from data that has not been seen. I mean, this is what you want. You don't want to test a network with examples that you already gave. I mean, there is not really gain on that, no? Because if you gave particular example and then the network is telling, oh, this is the output for that sample, well, of course, you gave it. But the idea is that you can provide in that stage data that has not been seen by the network, and still the network is trying to make a simulation and tell you what should be the output, okay? Well, in terms of the activated functions, we just before saw the sign, which is going to be either, well, this is actually, this should be, I'm going to call this a step. Sign something is like this, no? Going from -1 to 1. Okay? However, different activation functions can be used, and then we are going to come back why the reason of having this different, no? But you can have semilinear or sigmoid functions, okay? As well, to process, in particular, neurons, the information. Okay. Okay, so let's talk now about single-layer perceptron. Well, this kind of architecture was proposed by Rosenblatt in 1957. In this case, we use a logic threshold function as well for classification tasks. So the idea is here that we can classify between two different classes, okay? And we are going to use for that discriminant functions, okay? So the general definition for, well, this discrimination function is going to be like that, no? If, let's say that we have a function, g sub I, for each class Si, the classification rule would be that U, which is a particular input, which belongs to a particular class, if and only if the discriminatory function for that input it's bigger than all the others discriminatory function for the same input, okay? So basically, imagine that you have one input, then you are going to evaluate that in the different discriminatory functions. The one which obtained the biggest value is the class for what to what this input belongs, okay? That's all. But now here in the single layer perceptron, and particularly for two classes, you can also reduce the problem of the formulation as it's shown here. You can say now that the class for U, it's going to be S1 if GU it's more than 0. Why? Because, well, obviously this value, it's going to be bigger, therefore belongs to that classes, for having something bigger than 0 in G. Okay? So if G is bigger than 0, it's going to be class 1, otherwise it's going to be class 2. Okay? So maybe here you can note the similarity in terms of finding a threshold, no? If it's more than or less than. So the discriminant function here, basically it's going to be the same thing. You're going to have an input. You are going to be weighting all the components of the input by different parameters or weights. Okay. Well, particularly we said before more or less than 0. So when this function is equal to 0, is indeed the border. It's where the hyperplane or the linear it's going to go through. So we call this hyperplane because you can have actually more dimensions, but if you have only 2 dimensions, it's going to be one line. Similarly, as McCulloch and Pitts models, these are appropriate only for classes which are linearly separable, otherwise not. And then the problem is to find the hyperplane which discriminates 2 classes only. Okay? So it's something like that, no? To say that you have a few samples which belong to one class, a few other samples which belong to another class. If you are able to find this division, well, the problem is solved. If we consider the logic and function as before, well, we know that for 0, 0, here the output was 0, the output was 0, for 0, 1, for 1, 0, 0, and for 1, 1 was 1. Therefore, you could say, okay, well, like this, or maybe like that, whatever. There are actually different possible solutions which satisfies that division, no? And as we anticipate before, when you have an exclusive O, we know that the output here for 0, 0 is 0, for 0, 1 is 1, for 1, 0 is 1, and 1, 1 is 0. Therefore, as you can see here in the plot, it's not possible to find a line which divides these 2 different classes, okay? Therefore, you cannot solve this problem using a single layer perceptron because the problem is not linearly separable, okay? It was known that you could actually solve that problem using hidden layers, using additional neurons, structured in different layers, okay? But the problem then was not knowing that was possible. The problem was how to learn those weights, okay? Because the single layer perceptron learning rule works for problems linearly separable when you have one layer, okay? But when you have more layers, the same rule doesn't apply. We are going to check a different rule for that, okay? That was introduced later. Okay, I think we already mentioned this. I'm going to go next. We mentioned this as well. Okay. Okay, so if we see here the learning rule for the single layer perceptron, so we are going to start here. No? We can compute the perceptron output by, as we said before, multiplying the input for the weights. Well, in this case, we do not have the summation because it's basically written down as vectors or matrices, if you want. Therefore, the summation is implicit when you multiply different rows and columns. No? And then you have a G, which is going to be the activation function, which is going to, well, in this case, step, no? Or sign. Why? Because the output is going to be -1 or 1. Okay, so you are going to have something like this, no? -1 or 1. So you have the output, y hat, and white, the target, what we want to have in the output. Okay? Now, this, the weight, is what we said before, what we had to adapt or change in order to make the network to have a specific behavior, what we want to obtain. Okay? So the process here consists that, I'm going to jump here, that iteratively we are going to be modifying those weights, okay? Which initially could be any value, okay? To say random, for instance, or an arbitrary value. And then in every iteration, you are going to change the weight by something which is called delta value. Okay, so you need to compute the delta for the weights in order to update them for the next iteration. Okay, and how to calculate this delta? Well, as shown here. Okay, delta for the weights, it's going to be, I'm going to start here. Sorry, I'm going to call this. If you consider the target minus the output, it's a way to compute a simple error, no? You're going to compute the difference between what I wanted to obtain and what I got, okay? And this error, you are going to multiply for the input value, what came to the particular neuron, and a value which is called learning rate. Okay? Sometimes also called step size. Okay? Well, alpha is a value between 0 and 1. Okay? It's a rate. Therefore, it's going to, as you consider, it's going to be multiplying the error that you compute for something between 0 and 1. In simple words, this rate is going to make that value smaller or bigger. Well, or it's going to keep it as it is if it's closer to 1, or it's going to make it smaller if it's closer to 0, no? At this point, we have only that parameter, well, almost that parameter. But a problem that is present all around in artificial intelligence and machine learning is the, I want to say, massive number of parameters that we need to set all the time. Okay? And parameters like this, because there is not necessarily a known best parameter to choose. Regularly, in this kind of problems, you need to find or tuning or trying different values to see what is actually best for that particular problem. Okay? And here, if you think about that parameter, you are, as I said before, you are going to be modifying the error, no? And I'm gonna use this example that I try to use every term, though. So imagine now that you are now in this room. All the floor here are possible solutions, but I'm gonna try to find where is the highest point in this room. Okay? Every single position in the room is a possible solution. Obviously, some of them are better than others, no? So for instance, if I'm here, this is a possible solution. This one, which is another one, is better or worse? It's worse, because actually it's higher here. So this is a better solution. But both are possible solutions, no? I can go through, maybe going up, and then, well, I can explore my solution space, okay? And find different, and then in some point maybe you're going to find something which is good. That it is. The point is, when I finding iteratively different solutions, I'm going to be doing steps in that solution space. Steps. Oh, this is actually worse. And that's related with the step size or the learning rate. This step is going to be a huge step, maybe even huger, or it's going to be a small step. What would be the consequences of having a very big step or maybe a small step? And pros and cons to say. Sorry, say again. That is true. Smaller steps going to take longer time in order to explore. That is correct. That is good or bad? Or maybe both. Yeah, for the time conserved is something bad. I agree. Any other concerns about having huge or smaller steps?
If the step's too big, and say you want to find the lowest point, you could be on the tall area there.
Okay.
Just take a massive step, so like up there, and you miss the shallow spot here.
Sure, but that is something good or bad? That is bad. Okay. Well, it's bad if this spot are good solutions. I agree. It's good if this spot are making me wasting time. So you know what? Any other concern or pros and cons that you may think of? Well, certainly the time is an issue. But true. But if you go to the other extreme and then just allow very huge steps, indeed could happen. Well, here you need to think that you can go through. Let's say I'm going to try to find the minimum value error instead of the maximum value here. No? So imagine that I allow to have huge steps, and then, as your classmate said, maybe make a very huge step here. And imagine that there in the middle, there was a huge hole. I never realized about that. Okay? So, actually, in order to explore and moving from different sections, that is actually good, having, big steps. But having a smaller step is also good because it's allowed to explore much better a particular region, but take more time. Okay? So in both there is pros and cons. Regularly in multi-layer perceptions, which are more used, learning rate values are something like 0.01 or even smaller. Okay, regularly you use a small one, but then you can think of having, oh, what if I put 0.00001, much smaller, no? And well, the thing is, there are no real right values in advance. It's something that you need to test and see how the network behave when you are trying to train in it, okay? I just make this pause in that parameter. I guess, to be honest, that parameter is not even that important in the single layer perception, okay? But it's an easy way to explain it now, since we have only one parameter, and then it's going to be again. You are going to see all these equations all the time, okay? Okay, in simple words, if we consider these deltas, delta is going to be 0 if the output, the predicted output is correct. That obviously makes sense because this error here is going to be 0, given the subtraction, no? If I obtain what I wanted, it's 0. The error is 0, and therefore the delta is 0. O is going to be plus 2 times the learning rate times the input. If you wanted to have a 1 and obtain a -1, or negative 2 times the learning rate times the input if you wanted to obtain -1 and obtain 1. Okay? So again, you start to change the weight iteratively until this is going to converge. Okay? And it's actually known that the learning rule of the single layer perceptron is going to converge if the problem is linearly separable. It's going to converge in a finite number of steps. Okay? If not linearly separable, it's pointless. You're going to be like jumping from one to another. One side to another. So it's not what we have seen yet, but just to give you an example of how this should be. No? So imagine now that you want to use a network to train or learning about this data set. So in this data set, you may have different instances of cats and dogs. Okay? So basically, you are going to pass these images or data to the network, and what you expect to have here? Well, to recognize if it's a cat or dog. But here, you can give, in the data set, you are going to say, well, set 1 means cat, and set 0 means dog. But you are going to tell with examples, okay, look, this is what I want to obtain. This is my data set. When you see a cat, you put a 0 there. But obviously, not all the cats are the same, and not all the dogs are the same. But you can give examples, okay? And then, when you have adapted these weights and you know what is going to be the right weights in order to divide these classes, you can use, remember the second stage, simulation. So after training, you can use it for simulation. And then you say, okay, if you see now this image, what is the value of Z? You can ask the network what the network should say if it's rightly or correctly trained. What should say? Is that correct? Actually, no. It's a dog. It should be 0. Okay? Pretty much like that. Here you have dogs, here you have a cat. Then tell me, what is this? It's a dog. What is this? It's a cat. And so on. Okay? So quickly about the historical context, I said, we mentioned a few things about it now. We said that we have a time between 60s, 70s, and part of 80s, in which neural networks were actually people gave up, no? Said, okay, no, this is actually not useful. We cannot use this to solve simple problems, therefore seems not to be the next for us to use. Particularly funding agencies, no? So no money for neural network research. And as I said before, well, obviously, they prefer what you are investigating now, no? You're working with these kind of things now. Mentioned as well, they at that point they knew that they could solve the problems with a two-layer neural network, but the problem is how to learn the right weights through examples. Okay, because again, I want the network to tell me the output of data that has not been seen. Okay, and this was discovered, I'm going to say, in 1986 by Rumelhart. Discovered because most of the time the solution is attributed to him. Nevertheless, a few years later has been shown that Verbus in 1974 did exactly the same in his PhD thesis. Okay? And the solution for that, instead of having a learning rule that modified the weights or compute the deltas based just in the simple error, the extension of that is to compute deltas by using gradient descent. Okay? We are going to show how to do that as well in this part, which is called multi-layer perceptron. I'm good in time. Okay. I assume that you regularly have a break with Oliver, and I assume that is after 6. No, of course not. let me go through multi-layer perceptron. Hopefully, all of that, and then we make a break. It's going to be after 5:30, but hopefully not that after, not late. Okay. Good. Just as we said before, no? It was known that neural networks could solve the problem to simulate any logic function. So, for instance, if you consider the exclusive O, you could solve this using, well, and not or, which will be similar to express that network with those weight and those bias. The bias, I didn't mention that before, but bias is, as I said, is an additional input which value is always 1. It's true, but that every bias, remember that this additional input is connected to every single neuron in the network, is connected to every single network. Therefore, that connection also has a weight. Okay? So, this is what is represented here, no? That weight. Which can be summarized as the weight, no? Because the weight times 1 is the weight. Okay. So again, it was known that it was possible to solve it with a 2-layer network. But again, how to train the network in order to learn these weights automatically, okay? Well, this is exactly the same multi-layer perceptron that we shown before, okay? And I'm going to read the definition, and then we are going to say something, okay? So the definition of a multi-layer perceptron is a network in which its neurons are organized in successive layers. Layers. Each layer receives inputs from the previous one. Or external, okay? And send its output to the next layer. Okay? There are no internal connection in each layer. Therefore, there are not these connection. Or like this. Not like this. Okay. Okay? So, a multi-layer perceptron is organized in layers. In that case, how many layers? I want to say 3 layers. How many hidden layers? 1. You could have more, okay? You could have more hidden layers. The input one and the output is going to be 1, but the other one is going to be all the one in the middle. In this case, only 1. Okay? The layers are fully connected. Means that from every neuron in one layer, there is a connection to every neuron in the following layer. Okay? Again, it doesn't need to be like that for every single neural architecture. Not really. This is for multi-layer perceptrons. Okay? The there could be any architecture you think of. There could be different topologies and so on. There are quite a few different, okay? But in this case, it's this is the definition, okay? Okay, something that you are going to need to do in order to evaluate the neural network, first to compute the error and then later for simulation, is something which is called feed-forward propagation, okay? Which means that you are going to provide the network with particular data, inputs, and you want to see what is going to be on in the output, okay? This very small example is going to be showing this, no? So here, I'm going to start showing, just a second, this. What you see there underlined, it's basically what is going to go out from what neuron? From the inputs you said? I said no. That is going out from what neuron? Well, the input is, this is the input. So actually we can call it like this, A1 if you want, A2. From neuron number 3, correct. Because if you see, the first input, it's multiplied by this weight plus second input multiplied by this weight. So the input, each of the components, it's going to be weighted by the weight value or parameters. You are going to make the summation, and then you are going to send that to the activation function. So you are going to compute, let's say like this, no? This is the, and this, something like that. Okay? Now, if we look at this, similarly, that is the output of what neuron? Number 4, yeah, that's correct. Because similarly as before, the input, it's going to be multiplied by the W14, which is this one, plus the second input multiplied by W24, which is here. And as before, that's actually computing the summation, but then you have G. I'm going to say something like this. Okay? Now, A5, which is computing this or this. Well, if you see in the equation here, all these, it's called A3. All this is called A4. Okay? So in the case of A5, same thing. We are going to take what is going out from neuron 3. We are going to multiply by W35. And what is going on from neuron 4, we are going to multiply by this weight. Then we add this, and whatever it's putting on this. This is actually R5. Okay? If you understood before how to propagate for one neuron, this is exactly the same, but in a network. Is that clear? If someone doesn't understand any step from there, please let me know, because otherwise you are going to be struggling in the coming slide. We really need that you understand that, otherwise the next content you are going to be lost. Is that clear? Okay, backpropagation. Backpropagation is a very well-known and famous algorithm. It's the one I said before that was proposed by Rumelhart and or Verbos in 86 and 74, respectively. And is the algorithm that was extended from the learning rule in order to allow multi-layer network to adapt the weights, no? In order to compute deltas for that kind of networks. Okay. Well, what they propose here is basically that you can easily perform a forward pass. That is indeed easy. Is what we just did to compute, to propagate from the inputs to the outputs and to see what is the output. Obviously, you need to think that initially, all these weights will not have the right value, no? You don't know the right value of these weights in order to get what you want at the output, okay? There are different ways to initialize them, okay? You could say, okay, let's make all them 0, okay, but very naive initialization, no? For many years, the approach was like choosing like random values from a normal distribution. So regularly you have the mean in 0 and a very small standard deviation. But actually that was not a smart way either, because that even though they were random values, as you were constraining the use of this normal distribution, it's to say you were constrained to an area which was sort of close or small from the space solution. There are quite a few other methods. So for instance, one which is called Guylian withdraw, which used to initialize the weight more variables to say what is the variability of the data, the input data, what is the number of neurons in the header layer, you know, that, and then distribute the weights across a different range for each of the neurons. Okay, that's a paper from 1990. You know, it's 30 years old paper, but it's much more effective in order to initialize the weights. Okay. And obviously, as I said before, if you consider whatever area your solution space, you want to start in the best possible place in order to start your search. Okay? So it's super relevant what is going to be the initial values anyway. Yeah, when I was a master student in 2005, I was writing my thesis. And I was creating some models which are called gray box models. I was stuck for 3 or 4 months when I was writing code, precisely because I was using the approach that I just mentioned, using this standard, the normal distribution with a small standard deviation around 0. I cannot remember how many times I changed it, how many nights. Well, before going to bed, putting to run the code, and the next day in the morning review if the model was already trained or learned something. Nothing. Again, trying different strategies, until just really by chance, because I attended to a conference and someone mentioned this paper or this different way to initialize the weight, and I said, oh look, that could be. I never tested between the old things I tested. I implemented that. I talked to the person who mentioned, and he sent me the paper. I implemented it in a couple of days. Then I started running in the night. Next morning, perfect. After 2-3 months, or maybe 4 months, I can't remember, I got good results just changing that. Is really, really relevant. Okay, and then I started to learn more about optimization problems and that kind of things, which are obviously quite connected to machine learning. That is another topic that we are not going to review this term in this course. Okay, again, we talk about the forward pass. When you perform this forward pass, you should not expect to have the right values at the output, no? Again, because the weights are randomly initialized, therefore you will get basically wherever, anything. Okay, nothing really related to what you expect to have. However, you can use that in order to compute an error. If you know what you get, you know what you wanted to get, so you know the targets, you can compute that error, no? Which is the difference. And then you can perform this backward pass. Well, based on the error, we are going to compute delta values for every single weight in the network, okay? And we are going to backpropagate those delta values through the network, okay? When we say backpropagate, it's because the weights are not modifying in the same manner if they are, so to say, in this layer, which is closer to the output, as if they were in this layer. Okay? The influence of those weights is different because actually those weights went through another activation and transfer function in comparison to the ones we are closer to the output. Okay? So in the same way that you think of you propagate and then use these functions, you propagate from the input to the output and then you use those functions to compute a value, you need to compute it back. Okay? Well, this is the easy way to think of backpropagation, no? In a small network first. Well, as I said before, you are going to have these random weights here and here. But then you can feed forward propagate and obtain the output of the network, okay? From there, you can compute an error, well, whatever the error function you use. And then with that error and delta values, you can backpropagate back to the network, okay? Well, the first direct consequence of the algorithm is that the functions here need to be differentiable, okay? Therefore, functions like step or signs are going to need to be replaced for functions like sigmoid, this one, or hyperbolic tangent, sometimes called tangent sigmoid as well, sometimes called, okay? Because of the shape is like a sigmoid, anyway. But they are both, they have both a similar behavior, with the only difference is the sigmoid varies from 0 to 1, like the step, and the hyperbolic tangent varies from -1 to 1, like the sine function, okay? Okay, that's going to be very quick. Okay, so in order to compute the deltas, which is now this is deltas. Okay. Well, you should see there exactly what we did before for the single layer perceptron, no? An iterative update of the weights. We called this before, I guess, k+1 and k here. And we have the learning rate, which is also there, the step size, and a modification, what is going to be the delta value, which is going to modify the weights, okay? And this delta, now it's going to be computed from the error function, okay? So for instance, in this case, we are using the median square error, no? Or mean square error. And this is something to consider for the step size or learning rate. We said before, no? If you have a big value for that, you can actually create this divergent or Gaudy behavior, because you are going to be actually computing the gradient. And small, number is actually good for convergence, but with the disadvantage of the time. You can see there, I mean, you're going to be going in that step down little by little, okay? And yeah, and if we need to come back quickly to this way, this is just a reminder. I assume that most, if not all of you already have seen derivatives in calculus or mathematics. But basically the derivative of a function is the slope of the tangent in any particular point. Okay, so if we have the function y here, this, which is the slope, is actually identified as how much change y and how much change x. You can write this delta y, delta x, but in practice we write this like that, the derivative of y with respect to x. Okay? Now, a partial derivative is basically exactly the same, but you do that with respect to one of these variables, and you consider all the other variables to be a constant. Okay? Sorry. Okay. Now, let me see the time. Okay. If we consider this network, this two-layer neural network, which has a sigmoid activation at the hidden layer, and actually not all, well, this is the hidden layer, and should say hidden layer and output. We also have a sigmoid in the output here. We could know that, well, that we have, well, the x here are the inputs, y are the hidden units, these are the weights for the that connect the input with the hidden layer, and these are the weights that connect the hidden layer with the output, for the ones here. B, I, and C are bias. Okay. Well, we can say from this model and consider feed-forward propagation, we can say that U1, which is related with this here, it's going to be basically, well, this is the summation, no? It's going to be going to start here, no? The first input multiplied by the weight, this, and the second input multiplied by the weight, plus the bias. Or you can have 1 plus the W bias, which is that value, the same value. Okay? Therefore, you know what is going to be out from this neuron is going to be applying the application of G, and in this case, G, what it is? We set a sigmoid. We are going to apply a sigmoid here, and this is what is going to be out from Y1. Similarly for U2, okay? It's exactly the same, considering obviously the other weight and the other bias. Now, what is going to be the S value here, which again, this is going to be computing the summation. I'm going to start for here. It's going to be what is going to be out from this neuron, which is going to become the input of the coming neuron, multiplied by this weight, what is coming out from this neuron, multiplied by this weight, no? And plus bias. Okay? Similar as before, I can apply here an activation function, which in this case could be the sigmoid, and therefore you can obtain here set like G of S. Okay? This is the output of the network. Again, this is just as before, forward propagation, okay? I'm going to clean a bit this because I'm going to need to come back, especially these equations, I guess. and maybe the fewer, maybe. Okay. Okay. Well, the thing is, we said before, we need to compute the delta values. So it's the delta values is going to be the error, the partial derivative of the error function with respect to the weight. Well, if you see the error functions, obviously there are no weights there, no? I mean, not diagonally, no? But somehow they are there, not well, in an implicit manner, because these functions use the weights, no? So, in order to reach there, we use something which is called the chain rule, okay? This is the general way for the chain rule. And we are going to, therefore, decompose the partial derivative of the error with respect to the weight using the partial derivative with respect to the transfer function and the activation function as well, okay? I'll show you how. A couple of things that we are not going to be showing here, but we are going to use, is that if you have the sigmoid, as is shown here, okay, the derivative of the function sigmoid is actually this. Okay, you can easily even, you don't need even ChatGPT for that. You can also Google it. It's very easy. Okay, it's really short demonstration, but for time, no demonstration here. Okay, similar, if you want to check the hyperbolic tangent, derivative is going to be 1 minus z to the power of 2. Okay? So in other words, what that means, if this is the sigmoid, we are saying here that the derivative of the sigmoid is going to be the same function, 1 plus e minus s, multiplied by 1 minus 1 plus e. Okay? This is what we are saying at the end. Okay? Okay. Where I was here. Okay, so we already have stated that this is the forward pass. You remember? We can determine what is going to be the computation if we move the inputs towards the output. We know already what is the error. Okay. And now we are going to need to compute the different derivatives to see how we can actually calculate the different deltas, okay? Okay, so if the first one, if we compute the partial derivative of the error, what is the first function that you can see here? When you go back, remember, back propagation. The first derivative that you can see there is it's z, which is a sigmoid, okay? Remember? We said that we have sigmoid in the hidden layer and the output. That's what we have this. Okay? This is a sigmoid. Okay? Okay, but it happened that you have directly set here in the error function. Okay? So you can consider this part internally using the binomial square, no? Like set to the power of 2 minus 2 times z and t minus t to the power of 2, no? And then you will get exactly this. Okay, if you do the derivative of the error function with respect of z, okay? The square here is going to be gone with this 1/2, and the 2 times zi is going to be gone as well with this. Okay. Now, if you start to move toward, or back propagate towards the internal part of the network. Now you can compute what is going to be the derivative of Z with respect to S. So the derivative of the activation function with respect to the transfer function. No? And then this is going to be the derivative of G, which, as we said before, is a sigmoid. Therefore, we see, or we mentioned that this is the derivative, okay? We simply use it here. Now, we can keep moving to the internal part. So, the derivative of S with respect to y1, now what you need to look at is S. We know that S is computed like this, okay? And here we are going to compute the derivative of S, the partial derivative of S with respect to y1. Oops, sorry. With respect to y1. Therefore, this is a constant value, which is in the derivative is going to be gone. This is a constant value which is going to be gone. And this is the one multiply that one. Therefore, the derivative here is that value. Okay? And the derivative of y1 with respect to u1, which would be for that neuron the partial derivative of the activation function with respect to the transfer function, well, this is also a sigmoid, so it's actually the same pattern as here, but in this case with y1 instead of z, no? Okay. Now, if we want to compute remember the error is going to be computed here, no? If we want to compute the derivative of the error, but now not with respect to z, but rather with respect to s, well, this can be written like the partial derivative of the error with respect to z, which is the function which is actually coming next, times the derivative of the z or the activation function with respect to the transfer function. Okay? And this one, we have it here. And this one, we have it here. That's why this is the result. It's basically the multiplication of both. Okay? Similarly, if we now want to compute the partial derivative of the error with respect to B1, and this is actually a delta, you know, because B1 is a weight. Okay? Well, similarly as before, we can say, well, the derivative of the error, the partial derivative of the error with respect to Z, with respect the partial derivative of Z with respect to S, and partial derivative of S with respect to B1. Well, this is exactly the same as before. And the partial derivative of S with respect to B1, we need to go to S again. And now make the derivative, the partial derivative with respect to B1, no? Therefore, this is everything is a constant except that term, and which is next to this is y1. Therefore, is same as before times this term, which is y1. Is that clear? Okay. Well, you can do similarly for B2. But if we focus now in away from the input. Before computing away from the input, we need to compute the partial derivative with respect to that activation function, transfer function. Sorry. So this, as using the chain rule, Similarly, we are going to write this as the partial derivative of the error with respect to z, the partial derivative of z with respect to s, the partial derivative of s with respect to y1, which is the coming function, and the partial derivative of y1 with respect to u1. Okay? So if you look at that, if you look up that change rule, what I want you to put attention is that you are going to be going through the different functions when you are backpropagating. So the first one is actually z, then s, well, not b because b is not a function, it's a weight, but y and u going through. Okay? As before, we have already this value. We also have this computed here. This is B1. And this similarly knew it from here. Okay? Now, with all this, you can compute the delta for that weight. Okay? How you can say, well, the partial derivative of the error with respect to this weight, which is going to be the delta, how we are going to modify that weight, it's going to be the error with respect to z, this z with respect to s, the s with respect y1, the y1 with respect to u1, the u1 with respect to w11. Okay? Just as, well, what is in the previous line is exactly this, or if you want, exactly this. Okay? So the only missing value here is this partial derivative, and for that you again need to go to feed-forward propagation and see that u1 was computed like this. Okay? And you need to perform the partial derivative with respect to w11. So this is going to be a constant gone, constant gone. This is going to be the term that is actually accompanying w11. So this is what is going to be here. Okay? Is that clear? Exam-like exercise. Is that clear? Yeah, let's make a short example here, and then we are going to make a break. Okay. So consider the network that is shown here with this small data set. So you have as input 0.35 and 0.7, and the output or target, it's going to be, the target actually should be here, is going to be 0.5. So given this input, you want to reach, to get that value in the output, no? We want to train the following neural network for one epoch. Obviously, one epoch is not going to be enough. One epoch would be one iteration. Regularly, you train networks for many, many epochs or iterations. Okay? And see what are the final weights for this one epoch here. The activation function is the sigmoid, and the bias terms are set to 0. The error is as defined here, same as before, the mean square error. And the initial values for the weights are showing directly here in the figure. Okay? Okay, so let's move quickly. Well, we can easily feed forward the inputs towards the output, no? So basically, sorry, just for simplicity, I'm going to call here A1 and set 1, A2, set2, A3, and set3. As the value which is, well, let's make it simple. A mean the value coming from the coming output from the summation. And set, in this case, is going to be the sigmoids, okay? The one which is going on. So the A value here is going to be, well, weighting the inputs plus bias, and then you know that the first input is 0.35, which is multiplied by 0.2, and the other one is the weight 0.2 multiplied 0.7, which is that input. Okay? Bias, we set at 0, 0. This is 0.21, therefore we apply the sigmoid to that, and the final value, or the one going out here, is 0, here it's 0.55. Okay? For the second neuron, similarly, we are going to multiply the first input, but this time for this weight, the second input, this time for this weight, the value is going to be 0.315. We apply sigmoid to that one, and the one going out from here is 0.858. The one here was 0.55. Oh, sorry. Okay. Now we can do exactly the same for A3 and set 3. For A3, we are going to consider what it was going out from here and multiply by that weight. What is going out from here multiplied by that weight. Bias 0 again. The value there is 0.687, and when we apply the sigmoid is 0.67. So that is actually the output of the network. Okay, when we propagate towards the output. Okay, we can now calculate the error because we know the prediction. The prediction was 0.67. We just did that in the, you can see I have kids. Well, anyway. We just did here in the previous computation. Oh, this is not the one, this one. Okay? There you go. And we know the target, no? The target is, we set 0.5 from the data set. Therefore, the error here is 0.014, okay? Now, for back propagation, well, here, by the way, sometimes alpha, which is the learning rate, some step size, sometimes is called eta as well. So sometimes you will see that Greek letter. Well, but what we really need to focus is delta values, because the other part of the equation is sort of trivial, no? And we haven't mentioned any step size, so please assume it's 1, okay? Okay, so I'm going to start from here, okay? We need to compute the delta for every single weight, okay? So every single weight is going to need to compute the delta values, okay? Therefore, every single weight we need to compute for every weight the partial derivative of the error with respect to that weight. Okay. And in the first case, obviously, the derivative of the error with respect to the weight 2, 3, which is the one here, we can decompose this using the chain rule as the derivative of the error with respect to set 3, the derivative of set 3 with respect to A3, times the derivative of A3 with respect W23, okay? Now, this one is what we are computing here first. Well, we can compute directly the partial derivative of the error with respect to set 3 because, well, set 3 is actually the prediction. It's actually, if you consider the error function, what is here, it's the output. And the output here, we said, is set 3, no? Is after applying the sigmoid. This one. Okay? Therefore, we know that the partial derivative of the error function with respect to the sigmoid, which is here, is going to be set 3 minus the target. Therefore, the prediction minus the target, 0.17. Now, the second component, which is the derivative of set 3 with respect to A3. Set 3 is a sigmoid, and we said before that we can just use the derivative like set multiplied by 1 minus set when it's a sigmoid. So we put the values here, and that is this value. And the last component is the partial derivative of A3 with respect to the weight to 3. And in this case, just as before, we need to see A3, which is here. And we are going to make the partial derivative with respect to W23. So this is going to be the component, okay? And we knew that set 2 was this value, okay? Now, having all the components, we can know what is the delta value. This is not the new weight. The new weight is going to be using the previous weight, the learning rate, the delta value, and this is going to be the new weight, okay? We can do exactly the same for this weight. I'm going to go really quick, possibly not stopping much. We divide because I want to focus in the weights which are in the other layer. But here we are going to decompose just as before. We already have this. We already had this, and this is slightly different. It's set 1 because we are here making the derivative with respect to another weight. That's why. But with the values, we can compute what is the delta, and with the delta, we can compute the new weight. Okay, similar to before. Okay, this is the one for this weight. Okay, we are going to need to modify that weight, W11. Okay, so in this case, also going to start here now. We can decompose the partial derivative of the error with respect to the weight 1, using the chain rule as is shown here. I'm not going to go for all the components. You already assume at this point you already know. Maybe important to mention though is, again, keep an eye and see that you are going to be going through the functions. No? So the derivative of the error is going to be using first the last function, then the previous, that's why we have set here and A here, and then you go to the previous function, which is actually set 1, and then the other function, A1. Okay? So you are going back propagating towards the weight. Okay, so similarly as before, well, to compute the derivative of A3 with respect to set 1, you need to check A3. And A3 with respect to set 1, this is the weight. This is the weight. And then set 1 with respect to A1, this is a sigmoid, therefore we use the sigmoid. A1 with respect to that weight, we need to check A1 with respect to this weight. So we have that value, which is shown here. Okay? Now, with all this, we have computed that before, I think in the previous, in one of the previous. But if not, well, these are going to be the results. This is going to be the delta, and using that delta, we can modify the weight. Questions? Because I'm not going to stop in every, you will find there the delta for all the weights, but it's similar or analogous, okay? Questions? Good. This is back propagation. So all the point here at the end, the whole point, either in single layer neural network or multi-layer neural network, the whole point is learning how to adapt the weight, how you modify the weights in order to get what you want on the output, okay? So that's the key point here. Okay, so there are all the delta values. I'm just gonna go through this. Okay, so I'm gonna make 5 minutes, please. 5 minute break, and then we come back to close with the last one, which is very important, interesting, and relevant. Hello, hello, hello. Still not working. Okay. 45 minutes to go, so it should be fine, I guess. Okay, this second part is going to be mostly focused in neural network design. I guess we are going to quickly go through other architectures, but the main part is the design, okay? Obviously here I assume that you already know how artificial neuron works. You already learned that, and you know how artificial neural network works, how propagate information, how it can adapt the weights in order to get a behavior, a specific behavior, or satisfies our criteria, okay? Is there any question from what we have talked before? No? Okay. So let's talk about neural network design then. Okay, so what we are going to be describing here is a methodology which consists of 5 different steps, okay? So the first step, as you can see there, is exhaustive analysis of the system. I'm going to anticipate. The second one is preprocessing. The third one is design of the neural architecture. Then we are going to have training, and then we are going to have testing, okay? These different steps are indeed important because, as I said at the beginning, a neural network is, well, you possibly have seen and have heard about them. They are, I'm going to say, broadly used. They are used in many different domains, applications, okay? And they work pretty well. But you need to be careful. They are not silver bullets. They are not really the best model always, okay? For many of them, of course, yes, and they can simplify our life estimation, etc. But there are a few considerations that we need to take into account before deciding to use them, okay? Or once we decide how to use them, okay? The first step is exhaustive analysis of the system, okay? Remember, the neural networks are models. Just like any other model, there are a simplification of the reality. Okay, they try to model the reality in a way that you can actually make a read from that. Okay, but as is a model of the reality, they obviously have some error involved as well, which you want to minimize. Okay, so when you should take into account what system are you going to try to model using this neural network. Okay, some things that you are going to take into account in first place is, well, what are the variables involved in the problem? What type of variable? What is the number of variables? Okay, how many of them are going to be inputs? What is going to be the desired output? Okay. The main idea here is that you possibly try to reduce the number of variables, trying to simplify the model for that system. Because not because you have a data set means that you need to use every single variable there. Depending for what you want to model, maybe some of them, a subset of them, should be considered. Or maybe there could be variables that are related between them, or, and then maybe you could sort of simplify the model. Okay? Then the second question here, the second point, which is possibly the most important question, okay? Is it really necessary to use a neural network? Then one really should think if there is any other model available. So for instance, if I want to determine, if I want to throw this pen and I want to determine where it's going to fall down, what is going to be the position, should I use a neural network? Well, yeah, I could, certainly. But the point is, there are other classic models, phenomenological models, which taking into account the velocity, the angle, the mass of the object, and so on, can determine with an equation, which is also a model, by the way, it's a phenomenological model, and gravity and so on, they can determine where this object is going to be landed, okay? It's a model. They also may have error, okay? But certainly, these models, phenomenological models, were built by experts in the domain, considering variables that are present in those domains. And there are, well, that's another way again for phenomenological is white box model. No? Therefore, every single parameter there makes there is a relation between those parameters and the domain they are modeling. Okay. And that matters. That's important. That the error at the end is going to be possibly minimized. They are going to be easier to generalize as well, and so on. Well, but what if you don't really have any phenomenological model? Then you may think of use an empirical model. And that's why we say here that the neural network is the best second solution. You should start thinking if there is something else which actually is more convenient. If not the case, okay, maybe you jumped into this. Okay. Another thing is you may be tempted as well to use a neural network for problems which are easy in nature. So it's as former professor of math said, you don't wanna kill a fly with a bomb, you know. So this kind of tools are really good, particularly for, well, you can take the most from when you deploy them in complex problems. No, if you wanna, I don't know, compute an average of whatever input, maybe you don't really need it. Okay. Now, even though you can say, or maybe you decided that the neural network seems to be the solution to go, well, it's an empirical model, so it's highly dependent on the data. So that's the next question. Do you really have data? Do you have enough data? Do you have good quality data? I have worked in a few theses with students, and many times with the students who are already working for companies, you know. Many of these times, these students came to me and said, oh, Francisco, I want to develop this thesis, this problem, I want to apply a neural network. And when you see the architecture, how the solution looks great, but all the time my first question is this. Wait, before moving on, do you have data? Even a problem that is going to be applied to the company they work with, okay? So, no, that's not a problem. I want to ask, I'm pretty sure they are going to be super interested because this is going to be a great solution and so on. Okay. Please, can you come back with the data and then we move on? Well, most of the time happens that they never show up again. Or sometimes they show up many months later, say, oh, Francisco, sorry, I couldn't get the data because there is this issue, the owner of the data, the access to the data is restricted, or they don't really willing to give me the access to the data, and so on and so on and so on. So data sometimes seems to be something easy to get, but believe me, it's not, okay? Well, in research, many times we use data sets, no? So we try to find whatever available data set and do research on that. Yeah, true. It's super useful, but in real-world scenarios, obviously, not always data sets are available for trained models, and therefore, how you are going to capture that data, okay? How you are going to collect it. And you need to be careful when you collect it that the data is really representative from what you want to model, okay? So an easy example is, oh, you're going to make a study of, I don't know, how much is the salary of people living here in Sydney. And then I'm going to take data only to the richest neighborhood. That obviously that's not going to be representative of the whole population of Sydney. Okay? So you need to be really careful when you decide to use a neural model and the data that you're going to need for it, okay? Okay, step two. We just said step one, exhaustive analysis of the system. Step two is pre-processing. So once you think you know that you have data, which you can say, oh, it's representative because it was collected in a proper manner, that doesn't mean that all the data there is ready to be used. Okay? Still, you need to go to something which is called pre-process of the data. And even though, well, this is possibly kind of linked with the previous, no? You need to see that the quality of the data is good. Well, because many times you could say, okay, maybe I put a sensor checking how much was the speed of every car that was or went through Barker Street, whatever, or Anzac Parade, whatever street. And maybe you can have a look to the speed that you registered. And maybe you will see, I don't know, 30 kilometers per hour, or 40, 50, 60, or 70, 80, maybe overspeeding, but still. But sometimes you can see, I don't know, 300. You say, well, that's not really possible. Or maybe even a negative number. So, well, how it could be negative speed, no? So my point is, even when you put sensors, sometimes the data there should be either corrected, clean, or whatever, no? Now, neural network are black box models. Therefore, the parameter inside the weight connection, the weight values, are not really linked directly with the domain that you are going to be representing. It's not like the weight connecting the neuron 1 and 3 is representing the gravity when you are modeling, to say, throwing one object. No, it's going to be literally a random value which has no really relation with the domain. Okay? Well, therefore, black box model. You know the inputs, you know the output, but what happens inside, even though you can see maybe how this propagates, you cannot really find any relation between that and the domain. Now, what you can expect in a neural network is to perform interpolation, meaning that once your model is trained, you should be able to make inference inside or within the data that you provide. You should not expect that the network is able to do that correctly outside of the range of data that you're using, so which is called extrapolation. You should not expect that. There may be some cases, easy cases, in which that works all right, and that's okay, but you should not expect that, okay? Now, this is the point of quality and quantity is highly connected to correctly determine the parameters, the weights of the network. You cannot pretend to train correctly a network if you don't have enough samples, enough data to show to the network. Okay? Well, a few things that you should consider to pre-process the data. The first one is, well, visual examination or inspection of the data. So basically, you want to see how the variables perform or behave. As I said before, if you are working with speed, maybe you should not expect something negative. Okay, so in the tutorial that you are going to be doing next week, you are going to be working with a biomass, which is measured in grams. Same thing. You should not expect a negative amount of grams, no? Now, these wrong data are known as outliers, and then what to do with them depends. Well, the easiest is simply to eliminate them, so delete them from the data. But sometimes you could try to fix them, well, sometimes because maybe you don't have enough data, or maybe because the fix is sort of easy. But you really need to check the consequence, so to speak, or case by case, okay? Also, you could detect visually some correlations between variables, like correlations if you see that two variables are performing really similarly. That means that that is a possibility to simplify the model. You don't really need the two variables as input. Maybe you can actually decide a simpler model and work with only one of them. Another thing that you may consider is the normalization of variables. That is particularly useful when you have input variables with quite different magnitudes. To say, imagine that the x1, the first input variable, is varying from 0.1 to 1, and the second variable, x2, is varying from 100 to 1 million, whatever. If you consider the influence of those inputs when you propagate towards the output in the error computation, obviously the bigger the variable with the bigger range is going to affect much more than the other one, no? In terms of the error. Therefore, normalizing variables, what it does is take the variables and keep exactly the same behavior, but move them in a range of, well, can be between 0 and 1 or between -1 and 1. So the behavior of variables is going to be exactly the same, but within that range when you change that. Okay? Well, if the variation or the range are not that different, it's not really necessary, but if the range is completely different, it's something that you should consider. And then you should consider the normalizing at the output, no? So take it that to the original range. Okay, so step 1, we set, again, exhaustive analysis of the system. Step 2, we set pre-processing. And step 3 now is the design of the neural network, or design of the neural model. Well, so imagine here, this discussion is about multi-layer perceptrons, okay? So that applies for that kind of network. So we said before that the multi-layer perceptron is going to have a number of inputs, a number of units in the hidden layer, and a number of units in the output. Well, that number of inputs and output should be already determined from the step 1, no? When we analyze the system. What we want to model is going to be, well, basically the number of inputs and outputs. Okay? But what about the neurons and the hidden layer? Gonna assume here only one hidden layer. Okay? And why? Because actually it has been demonstrated that you could use a single layer, a single hidden layer to approximate whatever nonlinear function arbitrarily, with an arbitrary precision. It's not the most effective way, though. That's why later deep learning came. But it could be, okay? So here, and indeed many networks, even nowadays, use only a single layer, depending on the problem. A single hidden layer again. Okay, so what we say as a rule of thumb is that the number of units in the hidden layer should lead to a number of parameter of weights and W that is actually that respect this relation. So the number of weights should be less than the number of samples, data that you have, divided by 10. Again, it's not exact rule. I mean, it's just a rule of thumb, no? It's more or less. It's not there is no mathematical demonstration for it, no, at all. Just a good practice, so to speak. The number of weight of the MLP with NI neurons in the input, hidden layer NH and NO in the output layer, it's going to be determined like it's shown here. Basically, it's the multiplication of the connection considering the bias. That is why you have this +1 there. Okay? So, if you consider MLP with 3 inputs, 4 units in the header layer, and 2 outputs. The number of parameters or weights is going to be basically 3 plus 1, considering the 3 input plus the bias, times 4, the units in the header layer, plus 4 plus 1, the number of units in the header layer plus the bias, times 2, the 2 outputs. That is 26. Therefore, you could say here that you should have at least 260 samples to properly train this network. Okay? Again, rule of thumb. This is what I mentioned before. You indeed actually need only 1 header layer. And there are different criteria, but one very common is to use sigmoid functions or ReLUs. ReLUs is like this. Okay? In the header layer, and linear functions in the output. Linear functions mean that whatever is output from the summation, it's put in the output. Okay? That means linear. It's basically y is, my gosh, sorry. Y is equal to x. Okay? Yeah, there may be other combinations anyway. Okay, again, step 1, exhaustive analysis of the system. Step 2, pre-processing. Step 3, we design the network. And step 4, the critical one, training. Okay? As we said there, training the network is really hard process. Okay? The complexity of the error function in the solution space, considering that you're going to have a lot of minimum, maximum, this minimax point, etc. It's going to be a complex function to optimize. Okay. In this case, minimize the error. Okay. And during that process, you can face these problems which are mentioned here: underfitting, well, due to high bias, or overfitting or high variance. Okay. This may affect the capacity of the network to generalize. Let's see. Imagine that you have that data set, that set of points, and then you want to find a function to approximate those points. Well, using a neural network to approximate that, the underlying function, okay? What if you have something like this? It's a good approximation? Okay, bad, great. Well, visually we don't know much, to be honest. That's why we have some indexes later. But visually, you can see that that's the function. It's shown as a linear one. Well, actually, you could do better, no? So the problem here is what we say, well, training bias. Okay. So in this case, well, we said that bias referred to a systematic error when we try to approximate this real-world data. And the problem is that the network is not able to correctly approximate the underlying function. No? So that's why we call this is underfitting. Okay. So it's, in other words, it's giving us a too simplistic estimation. Okay. To decrease this, we are going to increase brutally. I mean, little by little. Not let's add 1 million neurons. No. We are going to add little by little some neurons in the hidden layer. Well, why the hidden layer? Because to create a more complex model, well, in this case, we should not modify the inputs or the outputs. That actually came from the exhaustive analysis of the system, therefore it's supposed to be set. But the numbers of neurons in the hidden layer is something that we can touch, we can modify. Okay? To create, again, a more complex and possibly efficient model as well. Another alternative is try to run the learning process again. It's not like you remember that I'm going to try to find maybe the minimum value when I looking for, or maybe doing steps here in this room. remember that I'm going to start in a random value, to say, random position, to say here. And then I'm going to start looking for other solutions. Well, maybe if I iterate, 100 times, 500 times, 1,000 times, doesn't really matter. Maybe I got stuck in some point. I cannot get out there. I can get stuck in a local minimum. I'm missing something or some other area which could be much better. So what if I restart the process and then randomly I start from another position looking for solutions? So you should try to reach a better local minimum by training a few times. Okay? We say here at least 20, again, rule of thumb. So, same point. What would you say about this? This is great. This is, well, it looks better than before. Does it? It looks better. However, I'm going to say this, it's too good. In this context, too good is also bad. Why? Because too good could mean overfitting. Okay? Well, if you have some points and then the network is learning the supposedly underlying function perfectly, that means that the network is sort of memorizing the data. So it's really good to tell me what is actually the output for whichever of these points. It's going to give me the perfect, so to speak, output. This is really good. It learns by memory, memorize. But also you should consider that, again, you're working with data. Data inherently always contains noise. And by doing that, you are also learning the noise which is within the data. Okay? Well, something that you should consider is to work with different sets, no? So once you have your data set, one strategy is to create these 3 different sets. One is called training, another one is called validation, another one is called test, sometimes called generalization. Okay? What is the point here? You should have these 3 sets in a way that they are all representatives. So the data should be from the problem I want to model should be contained representatively in the 3 different sets. The training data is possibly the biggest one. Well, there are different ways to make this, no? So you can say, I don't know, 80%, 10, 10. Or you can say, I don't know, 80, 15, 5. Or 60, 30, 10, 60, 20, 20. Doesn't matter. Well, maybe it does matter when you don't have a lot of data. Okay? But assuming that you have enough data, you can actually decide which one is going to be. But the point is, the training data is the one which is going to be to perform backpropagation. It's the one that we are going to be using to propagate through the network, compute the error, compute the delta values, and modify the weights. Okay? That is going to be in the delta values. That's going to be in the training set, sorry. Now, while you are training, at the same time, you are going to be checking the error of the network, but for a different data set, the validation set. That data is not going to be used to perform the error. To perform the error and then the deltas. You are going to use that data just to observe how the network is performing through the learning process with data that is not used to adapt the network, to data that has not been presented to the network, so to speak. Okay? I'm going to explain the last set in a second. The the idea here is to visualize the error function. When we say both sets, sorry, I'm referring to these two, training and validation. Okay? And then imagine that you can plot, you should plot the error function, or loss function if you want. You are going to be able to see that this is the error here for the training set. So again, you should expect that the error of the training set should be going down. Obviously, you are showing the samples, you are showing the data, you are adapting the network, the weights of the network, to match this data set, the training. So you should expect the error going down. That is what you are doing, minimizing using the gradient, no? But what if you plot simultaneously the error over the validation set? Well, you could expect sometimes to have a bit higher error, which makes sense because this is not the data that you are using to modify the weight, no? But you still can compute the error. And then you should go that, well, in the best case scenario, in a good scenario, you should be able to see that error is going down as well, closely to the training data, or the training error. But in some point, you will be able to see this, that the error over the training set keep going down, while the error over the validation set start to increase. What do you think that is happening there? Overfitting. From that point onwards, the model is too good, as we said before. From that point on, the network starts to learn so well the data that you are showing that start at the same time to lose the capacity to generate good outputs for data that is not used to modify the deltas of the validation set. So obviously, a good strategy should be to stop learning there, not going from that point onwards, no? Well, that's called early stopping. Okay, something that I expect you to use during the tutorial as well. Okay, other strategies, cross-validation, which I'm possibly not going to explain here much because I have not much time, so I'm going to keep going. But few aspects to consider, the weight initialization, well, as I said before many times, online or batch learning. I mean, you are going to be passing all the data and then compute the error backpropagate, or one data each time, one data point each time, compute the error backpropagate and so on. And other parameters like learning rate, the number of epochs, and so on. Okay, step 5. So we said before, remember, exhaustive analysis of the system. We said pre-processing, design of the neural model, training, and finally, testing and evaluation. Now that we have built our model, we have trained, we believe that's actually good, well, we need to really know, we really test it to see that it's actually working, okay? Well, this Occam's razor is basically pretty much related to the problem that we reviewed in training, no? Here is in the first one, there is an underfitting problem. Here, there is an overfitting problem. And this is likely to be a good training in which you can see that not every single point is well trained. So for instance, particularly here or here, there may be some errors, okay? But again, even though this misclassification, you could consider that in this case you are going to be learning the noise and error inherent in the data as well. So during the test, we are going to see what is going to be what are the capability of the network in order to, well, in terms of the performance with some data that has never been seen by the network. So if you remember, we said we are going to have 3 different sets: training, validation, and test. Well, even though the validation set was not used to compute the weight, somehow affected the training. For instance, because you use it to stop the learning in some point, no? When using earlier stopping. So even though it was not used to compute the deltas, it was affecting indirectly the training as well. While the testing set, not at all. It's a subset that has not been seen ever by the network, and you want to use it to see what is the generalization capability. I mean, it's still generalization within that data range anyway, okay? So you are going to have a small but representative tier set, and you are going to use in this stage, okay? So what about that model? Well, it's not perfect, as we said before. Well, but it's working okay. Well, obviously there are some errors here in some points, but maybe it's good enough. Okay. The thing is, even if you consider the first plot in which we have the linear function, it was hard to say, because this is a bit, well, visual inspection is something good, but sometimes it's tricky, because I could plot another figure slightly different, and the question is, would you be able to tell me which one is better? Possibly not, because visually it's hard to say, no? That's why we use actually indexes, okay? There are different, sorry, is this the right one? Yes. There are different evaluations index. In this case, we are showing, one which is called index of adequation, the root mean square, and the residual, this is the root mean standard deviation. I'm not going to give that many details. Basically, you need to work with the observed values, which are the targets. We're going to need to work with the predicted values, which are going to be the output of the networks. And yeah, basically that. I'm not giving many details because anyway, you are going to be computing this in the tutorial, exactly this indexes. So you will check that during the week. Other functions that you need to consider are some common loss functions as well. Well, you can use the mean square error, or MCE, the MAA, the main absolute error, cross entropy when you have 2 different classes for classification, okay? Again, I'm going to need to move quickly. Okay, I have 2 more minutes. Therefore, I'm going to go really quick to that part, but to be honest, this is something that anyway, I guess you can read from the slide, especially for the ones watching the recording later. The most important part was the part that I just finished, the neural network design, in the sense that it's going to be useful for you for the tutorials, but also for really working with neural network in some point and make some decisions, okay? Okay, but quickly, well, there are indeed other different architectures, okay? We have seen here, well, the single layer perceptron and multi-layer perceptron with more details. But generally, the networks are structured in something which are called feed-forward network or recurrent network. A feed-forward network is just like the one that we have seen, for instance, the multi-layer perceptron. In simple words, networks that take the input and propagate towards the output directly, okay? While in, I'm going to say, well, that's a description of this. While in recurrent network, you may have internal connections, okay? So one classic example, something like this, or the context unit, okay? Recurrent networks are very useful for time series because there is a sort of internal memory. So to say, if you have data which is, well, in a time series associated over time, the data that you are going to be given in time, in the current time, it's going to be kept somehow internally in the state, in the context unit, no? So when you keep going through T+1, T+2, and so on, the network is going to try to remember that time relationship, okay? Well, and the obviously well known nowadays, the deep learning models. Deep learning models are, well, basically, in simple words, network with many layers. Okay, that's the easiest definition here. Well, you can have something from 10 to hundreds of layers, or 1,000 even. Okay. Nevertheless, they are really complex network. A couple of deep learning models that are mentioned here is the convolutional neural network, which are specialized for vision tasks. We are going to review a bit of this as well, I guess, particularly about convolution in week 8 when we talk about computer vision. Okay. Also, well, you can have recurrent neural network in deep learning. Okay, as well, like LSTM. The thing is, well, due to the complexity of this network, they are really heavy for machines in order to learn. You really need to run the learning process for long hours. I mean, even some network that we use in research can be training for days or weeks. Okay. Just to sometimes realize that the training is not working, and then you need to start to play with the parameters and try again and so on. Okay? So the depth of the model is defined in terms of how many layers you have. So for instance, in this example that we have seen before, well, the depth here is simply 2. But as I said before, you could have a depth of even 1,000 layers also. So question, just to wrap up. If I put 1,000 neurons in a single layer, just like this, or have 1,000 layers, each with 1 neuron, which one qualifies as deep learning? Is any of this network a deep learning architecture? Well, true. Well, this actually is a known architecture at this point, I guess. So the second, no? Yeah, well, the first one is indeed a multi-layer perception with 1,000 units in that layer, no? So it's well, not even, because we don't have any output here. It's just a single layer neuron. Sorry, other side. So no, actually, that is not going to be good, not going to be considered a deep learning architecture. It is in the second. However, this is a very narrow architecture. Therefore, we should not expect anyway to have good performance in that kind of architecture, okay? Okay, this is the reference, what I have used for this lecture. And as usual, please, if you want to provide early feedback, early anonymous feedback about this lecture, please use that QR code or that link. Yeah, thank you very much. I went, no, it's actually 1 minute to 7. We can go 1 minute more. No, thank you very much. Muchas gracias. I'm going to see you next week. We are going to talk about reinforcement learning, which is important because reinforcement learning is what you are going to be using for assignment number 2. And it's going to be linked with neural networks as well. Okay? So thank you very much. Remember to keep progressing in your assignment, and the deadline is next Friday.